Just to get a little feel for the audience here, anybody here actually heard of CoreOS in the context of server stuff? Okay, great, awesome. How about things like Docker? Docker, okay. etcd? Less? Okay. How about, who here has like launched a server on a cloud provider, on Amazon or Google? Okay, all right. Now keep your hands up. Who here actually, wait, sorry, one more down. Who runs servers in some capacity? Like you have servers that are under your management. I'm sorry. Okay, all right, keep them up. Okay, over 10 servers, keep them up. All right, over 100 servers. Okay, all right, what do you guys do? How many servers?
About 1,200.
1,200 and? 500. Okay, actually we can do this. This is off script here. Wait a minute. Oh, maybe I shouldn't go off script. That's my project. Let me just, this is too good of a party trick that I have to try to do it. I'm going to mirror my displays if this works. Oh man, this is what I get for doing something I wasn't planning to do. Kill the display. Maybe this was a bad idea. The demo gods hurt me, so I'm going to stop right now. What I was about to do, while my display figures this out, I was going to go and launch 500 plus 1,200, 1,700 servers on Google, because you can just do that in like 5 minutes now, and it's kind of crazy that that's even a possibility. Oh, we just got it. Okay. Do it? Okay. If I do it, you guys have to remind me to shut them down at the end, because I might forget. I don't get to write code that often, so when I do, I like to show everybody the code I write. And so this is a tool called CoreOS that launches CoreOS on different cloud providers. So we'll do it on Google. How many? Let's see, 1,800. And then we'll set my cloud config to, is this command right? To examples auth. Here we go. So this will allow me to log into them. Okay. My tool does an OAuth against Google, and then the third leg of the OAuth back to my command line utility. Okay, now is my internet going to work? If you guys haven't used Go, it's really cool. And I'm not just saying that because I'm like a San Francisco hipster coder. I'm saying that because it is really actually handy. In my command line utility, I did the third leg of my OAuth back to my command line, and now each of those dots is a server coming up on Google Compute Engine. So we'll just let that run for a while and see what happens on the other end. Okay, back to CoreOS. All right, man, now it's not presenter mode. Okay, I'm going to do 3 minutes of downtime again just to get me back to presenter mode. Unmirror. Anybody know a joke? This happens. It must have something to do with the really long RGB cable up to that thing. No, it was right as you tried to do that. So you kind of have to fake it out. Yeah, I'm going to unplug you. No. Okay, give it 1 second. There it goes. Okay. Okay. So CoreOS is a OS for large server deployments. You can run it on small server deployments too, but the principles that we're designing are for running large deployments. Another way I like to put it is a platform for platform builders. What do you guys think? No? I don't know. Another one, I'm trying to get this one by our marketing team, but they're not taking it. The undercloud. Okay. And borrowing from our friends at Salesforce, I think if we're successful, we're the no OS. No operating systems don't matter after we're successful. So a little bit of background about myself. I was previously with Rackspace, helping build a cloud platform there. I joined through the acquisition of my first company, CloudKick, and before that, I was at Mozilla, helping take back the web in the Firefox 1.0 days. My team is a lot cooler than I am. They hail from a bunch of different big companies, kind of the team you would imagine building these types of systems. Guys that have worked on cluster management, at Twitter. Brandon, our co-founder, was on the SEAL Team 6, the kernel developers at SUSE. Rackspace, Red Hat, kind of the usual list. Our company is funded by these investors. We've gone as like VC funded as you possibly can. So why did we start building CoreOS in the first place? This was an article that came out in March oh, it's a little bit off the screen, but there's just this, if you put a server on the internet and you leave it there, like it will erode and just eventually get hacked. And that's just like the way it works today. And so when me and my buddies were putting our heads together to see what we could do that, one, could be a big business, but also be a meaningful thing in the world if it existed, we thought, what could we do to fundamentally improve the security of the internet? We think that would be a meaty challenge, and if it works, it would be a big deal. And so where we started was looking, going back to the browser days. Who here remembers 2003 when Internet Explorer was the peak of the web? Maybe that's a little too early for a lot of folks in this room. But IE used to run the internet, and there was these huge like Patch Tuesdays, and there's these windows where everybody was getting hacked and phished and like everything until Microsoft got their patch out. And this is what allowed Firefox to actually come out and become a lightweight, secure, web browser is what it's called. But what really trumped everybody is when Chrome came out. And what Chrome did differently than Firefox, it did a number of things, but one of the big innovations was how it applied updates. And what it does is it does this today, it just downloads the update and applies it, and when you launch Chrome the next time, you're just always running the latest version. It's kind of like a software as a service, but for a client application, okay? CoreOS actually does this today, and that's where we started out with CoreOS, and I wanted to bring that out just because Keith is here, and he works on the security for CoreOS, and Case, sorry. And anything I say now, I'm worried that he's gonna cringe. But I believe this automatic update was the biggest step forward in web security that we have seen to date, okay? And when Firefox and IE followed suit in this, not only do we have like the most secure front-end internet that we've ever had, we also have things like HTML5, just because these guys can go and like distribute updates to the internet and effectively upgrade everybody overnight. We got nothing like this for servers. For servers, state-of-the-art is get it running and don't touch it. So we thought if we could build a server OS that automatically updated itself, that we could unlock a lot of value. And that value is around performance, security, reliability, really just everything you get by running the latest version of software, okay? But this also freaks out every IT guy, like you might imagine, and that's why I think a startup is doing it and a big company isn't. It's so orthogonal to the way that people run their server infrastructure today that like, no, you can't do that. But if we did it, it would be a big deal. So we're like, hey, well, let's try to do that and see if it works. All right, so how do we build a server OS that updates itself? Well, one thing you can do on a browser that you can't really do on a server is take a downtime. But fortunately, people want to run their server infrastructure in a way that doesn't go down as well, but we sort of have to just rebuild how you run your applications all together. So I'm going to walk you through this stack. This is a very simplified stack, but essentially you have a base Linux OS, you have some sort of clustering thing on there, and then you have the way you package and run your applications, and containers being a good thing for that. So we'll walk into each of these pieces a little bit, starting with CoreOS and how it all works. So this is how it works today. You have things like RPM, which they download files, they restart processes, they edit configuration files. You really don't know what any individual RPM is going to do. And so when you run it, you need to sort of handhold it or write scripts to do it. But those scripts kind of work half the time when you have to restart things and see if it actually works. It's a non-deterministic way of installing things. App does roughly the same thing. Chef allows you to write Ruby scripts to do this for you. Puppet allows you to write Ruby in their DSL to help you do this. But these all kind of do a similar thing. They go and rummage around on your system, and hopefully it ends up in a state that you wanted at the end. And if anything goes wrong along the way, you're now in a manual process to go and fix that. Or with cloud, it's easier to blow away a whole server and start over again. But not many folks do that. So we just take a totally different approach to this. So the way distros work today is you have your application, and it fits on top of a AOS, and your versions of these different applications and everything you're running are up to the OS provider to give you. And if you want to deviate from any of that, you're kind of just SOL. You can install your own packages, but it starts to get pretty messy pretty fast. And so you have what this creates are these like every 3 to 4 or 5 year cycles where you need to do these major version changes, and it's a big painful process. What we do is we move the line. We actually just do less. It's a little bit clever. in that it makes it a lot easier to support, but it also separates sort of concerns here. We are the CoreOS. We're just the pieces you need to actually bring up a computing environment for your applications to run, and all of your applications are individually bundled with their own thing. Now, I do want to call out, this is pushing the problem around a little bit, because when you have that OpenSSL vulnerability, now you have 3 copies of it instead of 1 to patch, but there are techniques for handling that as well. So this part is the CoreOS, and this is where the containers piece comes in. So every container, you can package sort of all the dependencies that you need to run in that. Okay, so this allows us to swap out the base CoreOS on you all the time without breaking your application and your application dependencies. Okay, because what normally breaks during an upgrade are your applications and their dependencies, not the kernel themselves. And then you might be thinking, well, wait, what if you actually break like an interface in the kernel? Well, we rely on one thing here, and that's that the Linux kernel does not break user space, or at least it's not supposed to. And this is a quote from Linus. We do not break user space. Seriously, how hard is this a rule to understand? We particularly don't break user space with total crap. Very good Linus quote here. But the trick here is that the Linux kernel exposes interface to the kernel, which if we move versions forward, your applications will never break. Now, if your applications need to run on a really old kernel, well, that might be a problem. But because we're moving everything forward, we can actually keep it relatively stable. Now, if we do break the Linux kernel, we have all these techniques about how we actually distribute the updates through multiple channels and all of this to figure that out before we deploy it into a production system. So our actual update works like this. This is where we borrowed some concepts from ChromeOS. So in CoreOS and ChromeOS, there's 2 root file systems that are completely read-only. Okay? So it means the base OS is fully managed by the OS vendor themselves. We actually bang bits on the file system such that even as root, you can't mount them read-write. If you're really clever, you could figure out the bit to DD to cause it to go into read-write mode. But for the most part, it's fully read-only. And what that allows us to do is when we're booted onto the A partition, we silently download a whole new OS in the background and apply it to the B partition. So our updates flip back and forth atomically between versions. And this allows us to always know that you are in a consistent state. And by a consistent state, we mean we can do a signature validation, a runtime signature validation of the root block device to guarantee it's exactly what we say it should be. Your data then goes and is installed on this read-write partition. And so essentially we're swapping out the piece below you and not breaking your dependencies because your applications are all in containers. Make sense? Yeah? Any questions so far? So the question was, what happens if A or B gets corrupted? So before we call the patch successful enough to put you onto it, we'll do extensive signature validations, checksumming, kind of everything you would possibly need to do in order to verify that it is exactly in the state that we need it to be in. And if any of those steps fail, we don't move forward. And so that's, even sometimes like on hypervisors, they're doing weird things to the disk that you don't know, because they're poking the disk from out of band, and that will even detect. And so if you run CoreOS version whatever 400 on Amazon, you know that root file system is bit for bit identical as CoreOS 400 on your bare metal server on Google or whatever. And if you manage to boot it, essentially you can't boot a corrupt one unless something happens in the moment that you're rebooting onto the new one that causes disk corruption to happen. Okay. Next is clustering. So this is Fleet and etcd. So let's talk about etcd a little bit. etcd. So why is it called etcd? First, you could tell a product marketer to not name that one. It's like, etcd? Is that a knitting website? Like, what is that? So the reason we called it etcd is because it's /etc distributed. The idea here is that every server, when you have more than one, you need to start sharing configuration data and doing service discovery. The minute you have more than one, they need to start knowing about where each other are. And so if we're going to do that, let's do it in the most hardcore computer science-y way we can. So it's a highly available key value store for shared configuration and service discovery. That's kind of a mouthful. So what does highly available mean here? So when we mean highly available, we mean quorum is available for atomic writes, okay? So anytime you can write to etcd, we will guarantee, using a consensus algorithm known as Raft, that your write has been replicated to at least a quorum worth of machines. So this is something that's also implemented in things like Zookeeper. If you're familiar with Zookeeper, or inside of Google is a thing called Chubby. We actually built etcd sort of inspired by Chubby, and now the Google guys are using etcd in some of their open source projects, and we were like, woohoo, success. Like if Google picks up our stuff when we wrote it on their stuff, it's like, must have done it somewhat right. But so this is available in a 5-node cluster. This would be available. This is still available. And now we are unavailable. And again, this is unavailable to writes, to changes to the cluster at all. You could still read the existing state in the cluster. So highly available. So key value store. The way this is exposed is as just a simple key value store. You can run commands using our command line utility that do things like this. The database is currently this IP. Operations like the last one there, the set db master, that's the one that you need to have like atomically consistent throughout the cluster. If any node thinks at any given point, like node 1 is the leader and these other machines think node 2 is the leader, you could run into problems. So that's an example of one of the operations where you need the cluster to have consistency. Everybody has to agree that the current master is db0 in the case of this example, okay? It's all over HTTP, simple HTTP JSON protocol. That's one of the reasons we built it. Things like Zookeeper are a requirement for building any sort of distributed system, yet it's really built for the Java community, and there aren't a lot of good other libraries and other languages that are easy to use. So we were like, let's build the essentially like layman's version of not layman's, but the like easy version of Zookeeper, but still get the hard parts right. And so we exposed it over HTTP and JSON. And because of that, we've never written a client binding outside of the Go one yet. There's client bindings in every single language, just because it's rather trivial for people to build clients to talk to this thing. So for service discovery. So service discovery is interesting, and it's something that doesn't need to be truly consistent. So service discovery is when a machine comes online to tell all your peers that you're around. So an example would be like a web app server comes up, and you need to tell the load balancer that you should start sending traffic to it. That one doesn't need to be completely consistent. But there are certain operations that do, such as the database, and I'm going to walk through an example of how you would use this thing to do a database master election. Is this okay technically wise? I'm going deep. Okay. So here's an example. An application talks to etcd and says, where's my DB? And etcd's no database. Okay, I will wait and watch. So what the watch operation does is it's just an HTTP long pull back to a key, and that HTTP long pull will respond when that key changes in some capacity. All right, so now Postgres comes up and it says, who's the database master? etcd responds with, no database master, you're it. And then etcd writes out to that watching process, a database master has appeared, and the application would then reconfigure itself to be able to talk to that. Okay? This is about as simple as it gets. So now a second database appears. Is there a database master? Yes, a master exists. Okay. So that database now configures itself as a slave to the Postgres master, and it starts to heartbeat back to etcd. Okay? Now our first elephant disappears, and you're the master now, which then also tells the application there's a new database, and our application drops the table. I'm not sure why the application drops the table, but it sent the query to the right place. The master, the second one comes back, or the first one comes back, master exists, it is now a slave of the master. Okay? This is about master elections, or 101 here a little bit. What's happening behind the scenes here are these swap with value operations. Now these are the ones that actually have to be atomic. So this is saying, when that second Postgres comes up, it says swap services database master with like only swap it if the previous value is db1, okay? So essentially everybody comes up with, and they send a query to etcd with their known state, and if their known state is no longer true, the write would fail. Following me? So they're saying, in this case, it was set to db0, and that second operation is going to fail because the value is database 1, okay? You see? All right. That's like the atomic part. All right, so that's etcd in a nutshell. Questions on etcd before I move forward? All right, keep going. Fleet. So fleet is what happens when you take systemd on one side, which is the init system that actually controls processes, and then you plumb it into etcd on the other side. So what it effectively gives you is a distributed init system. It allows you to schedule processes across a set of machines, and etcd will guarantee that one of the hosts is actually running that process, okay? Here's a bunch of garbage on a slide. This is an example systemd service. In this case, it's just sleeping, but it's being started with fleetctl. So this is saying, this is a daemon. This daemon happens to sleep. It gets launched at a cluster level, and now it's running on that server, 169. And this is something that demos a little better than Slidewares, which hopefully I'll have a couple servers we can demo on here. But the point is here, if that machine, 169, disappears, that unit will still exist somewhere on the server. It'll get rescheduled to another machine at a cluster level because of all the semantics that we have between etcd and systemd inside of Fleet. Okay? That's a big gloss over. It's way easier to show this than it is to explain it. But imagine you just schedule a process at a cluster level instead of a host level. And even across machine failures, that process will be rescheduled. You will lose state, which that is even a problem we could solve. But to date, you lose state, and the process will be picked up and started running somewhere else. Okay? All right. It works. Hand wave. Okay. The next piece is Docker and systemd. So systemd, what systemd actually does, and I heard Docker was covered in another talk, so I won't talk too much about Docker specifically. But in case you're not familiar with Docker, Docker packages and runs a Linux container for you. What systemd does is it's the actual init system that does things like mounts your storage, it sets up your networking, and also runs processes. So here's a really trivial example of another systemd unit file just for mounting some storage. But you could also write a systemd unit file to launch this is the Docker. This is saying, launch this Docker run after a Docker service has started. If you're not familiar with systemd, it's something that is coming onto all Linux distributions. RHEL 7 shipped with it, which means CentOS is with it. Fedora has been using it for a while. CoreOS has used it ever since we existed. Debian has voted to switch. Ubuntu, Mark Shuttleworth put out this thing saying they chose the wrong thing and they're going to switch to systemd. And so like everybody is switching to systemd. It's this very weird thing in that like kind of everybody hates systemd, at least on the internet, for some reason. We've been using it. It works fine. I think it's kind of comes from a place of it doesn't follow the traditional Unix philosophy of being like one thing and do it well. It's the init system, so it kind of does a bunch of different things, and they bundled it all into one and just made decisions for you. But systemd is definitely something, if you have to deal with servers, you'll have to run into at some point here. So that's the systemd piece, okay? Well, what's the big picture in all of this? This is where I'm going to step back. Before I move forward, any questions on the individual components of this stuff? Anybody interested in anything in particular? etcd, systemd, Fleet, Docker, CoreOS, all these things? Nope? Okay, then I'll just tell more jokes. So what is the big picture in all of this? What are we actually building towards? This is all interesting technologies that they are coming around. People seem to be talking about them. If you haven't noticed, containers have been in the news recently. But there's also a lot of other things going on right now for some reason. There's Docker, there's LXC, Fleet, etcd, systemd, all these things I keep saying that end with D. Mesos Go seems to be part of this for some reason. Kubernetes, people heard of Kubernetes? It's a cluster manager that's also being built. It's like, why is all this stuff emerging right now? I've been really just trying to figure this out. Like, it's not like Docker is definitely part of it and might have, I think, triggered this, but there's more to do than just like running a container. This was a blog post that that came out in when was it? In July. Now this is a real head scratcher if you look at it. I mean, look at those names: Microsoft and Red Hat in the same on the Google blog. It's like a very confusing set of companies on this list. And if you scroll down to the end of the post, you see this usual list of suspects again. You know, CoreOS is on there, Docker, even Golang is mentioned, the Go source code. And then I saw this guy, Urs Holtz. I recognize that name from somewhere. Where have we seen Urs before? So I've been trying to figure this out. Like, what is actually behind all of this, like, stuff that's happening? I went over to the Docker website. This is the Docker homepage. I actually took the screenshot this morning. And it says an open platform for distributed applications and developers. Okay. And then I went over to the Mesosphere website. You know, the one that stuck out to me here was scale infinitely. Okay. So we keep talking about scale and containers and clustering and ERS. I'm trying to piece it together. Then I remember this paper that came out in 2009, The Data Center as a Computer, an introduction to the design of warehouse scale machines. What's a warehouse scale machine? I'm not sure, but it sure does sound cool. And look, here's our friend again, Urs. He's up there on that paper. I flip into the abstract, and it says, you know, fault-tolerant computing, cluster computing, data centers, distributed systems, cloud computing. And then it hit me. Google is behind all of this. Google created cgroups, which is the thing that is one of the key components of a Linux container. They built Borg on them, run thousands of containers. Then they built a public cloud, but they forgot how the rest of us run our infrastructure. And instead of trying to make their cloud more easy to use for the rest of us, they decided to change how we all run our infrastructure instead. And so what's really happening is we're just all rebuilding Google's infrastructure. And if you look at all of these components, what is this warehouse scale machine? It's you add more servers to get more capacity. Any individual server doesn't matter. Think about apps, not servers, rolling upgrades, no more maintenance windows, and really smart software with dumb hardware. And kind of all these components, if you really think about it, is what we're building towards. And if you read the warehouse scale machine paper, it has a lot about the actual mechanics of a data center. But the way you run your software on top of that data center is kind of all of these principles. And I believe that all that we're emerging right now is at some point we're all going to have our own mini little Borg, our own little mini Google infrastructure that you'll be able to run in your own environments. So if you want to try it out, try all this stuff out, these are some of the cloud providers, kind of all the major ones so far. DigitalOcean we just announced, and everybody was pretty excited about that one because you can get a really inexpensive VM there. So I'm going to pause here, and then I wanted to, if we have time, and we have time, to jump into actually demoing some of the stuff, getting on the terminal, if that's okay. Yeah? Okay. Questions, though, before I jump ahead into that? Anybody? All right, I'm going to do my flip over. See if this works. Somebody asked to have a question about this. I've said so many random, obscure things. Oh yeah, thank you. Well, we'll check on those. We'll see how they're doing. I just remembered on those machines, I turned off public IP addresses because I was running out of my allocation. So I won't be able to SSH to them. But this thing's coming around. There it is. Okay. Okay, let's see how many we got. There's the script. Let's just do this. Oops, list. See how many we actually got. I had to like use secret trails. We only got 450. Come on, Google. Like seriously, it could be way better. I normally get way more. I hit their QPS limits, and the product manager for GCE is like, email me before you do that again. But I'm like, come on, you're Google. You should be able to do that. So we'll shut those down, and I'll just spin up a little cluster for the purposes of the demo. But we can keep kind of throwing machines at this cluster I bring up after I demo it. Oops. Okay. Let's just clean this up a little bit. I don't know if you've had any other talks where they're messing with their PS1 during the talk. Okay, so first thing I want to call out is the cloud config. Core update. Okay, so the cloud config, you see that? Transparent terminals aren't too bad. Okay, the cloud config is, you can think of CoreOS as like a statically compiled binary, and when you launch that statically compiled binary, you have to give it arguments to run. And the cloud config are the arguments for it to run. And if you're on a certain version of CoreOS, every time you boot it, given the same arguments, it will do the exact same thing. Novel, huh? So what these arguments are saying is for, let's see here, on the update server, you can actually change the update server to point at different update servers. We host one just like any major distribution would host an update server, but you can point it at your own. On etcd, this is a little service we put up to help you bootstrap etcd clusters. If you don't have a system for doing service discovery, it's hard to bring up a dynamic environment without service discovery. It's sort of a bootstrapping issue. So we use etcd.io as like a hosted etcd server that you can use because etcd can bootstrap itself off etcd, okay? And then down here, this is just saying start etcd and start fleet on the server. This users flag, this one will definitely make Case cringe. This is the Unix user core. It will download and place the public SSH key for the GitHub user Polvi. And this is just a cute little hack to allow you to easily do SSO across cloud providers, because every cloud provider gives you a different way of handling public keys, where if we just pull it from your GitHub public key. Of course, you don't have to use this for your actual SSO. It's just like a clever hack that demos pretty well. So there's that. Before I get going, I'm going to get a new discovery token. So you just get them from discovery.etcd.io. This will say this is kind of all one cluster now, anything that can hit that. And then if their networking topology works, they'll come up. So I'm going to launch a small cluster here. We'll do this one on EC2. We'll do 5 and equals examples. What was it? Core update. So this command here is not printing out the dots. This is what stuff I can do if I don't actually publish a tool open source, if I just hack on it on my own laptop. This thing will actually block until the SSH ports are up. So it's sitting there pulling SSH, just waiting for the ports to actually be up, because when the cloud providers tell you your server is running, it's 99% of the time not actually running yet. And so you can't just trust their APIs. So this thing is sitting here pulling port 22, just like waiting for port 22 to come up. While we wait on that, I'm going to grab this token. You can put it in the browser and see if anything's there. This will start reporting the list of servers that have like pinged this discovery token once they're there. So, anybody know any jokes? Okay. Live demos take a minute, and Amazon is a lot slower than Google. I guess I should have demoed it on Google. I just wanted to show that we work identically on the different providers. Any questions to help me kill time? Yep. Go. I love Go. Oh, we got servers. So I don't have to stop. How much, again, I like showing people code I write because I never get to write code. And actually this thing back here, I implemented the BitTorrent protocol in Go, and it's like the perfect thing to like write that in, because Go with its concurrency patterns makes it so easy to like bring up a server and a client in the same code. So like with BitTorrent, you need to be a seeding peer as well as a client of the protocol. And Go's like the perfect language to write this in, because it's just trivial to like spin off one routine that's listening and seeding the data, and then the other ones that are actually fetching all the pieces. So Go is amazing. It's the perfect combination of, in my opinion, perfect combination, like the ease of programming of Python, but you get static typing. So if you've been using a dynamic language for a while, you feel invincible all of a sudden. And then you get, it's not as fast as C or C++, but it's way faster than Python or Ruby. And so you get, good enough speed that you won't have to rewrite it for performance issues later. So kind of concurrency, static typing, speed, it's like all go all the time. Okay, so I'm going to get another terminal going here. Okay, so I have two machines. So I'm just going to grab two, log into them, forwarding my keys so I can get around the cluster. Okay, so we are into CoreOS machines here. The first thing to check is I'm going to kind of go to the end of my demo, which is using Fleet, but start there. And that if this command works, it means if we see a list of servers, it means that the etcd cluster came up, then all the Fleet daemons on the servers came up, they registered themselves with etcd, and now these are all the hosts in the cluster that are able to do kind of cluster-wide scheduling of processes, okay? So this is like my test to see if all of this worked. Woohoo! We have 5 servers. It worked. Okay, good. All right. So before we dig into that, I just want to do some basics on like etcd and stuff. So etcd, we have this little command, etcd-ctl. So I can go set key, so foo to bar, foo, and bar is set. On this other server, I'm going to refer to see the 108 here, and then over here I'm on 104. So I'm going to refer to the servers as that. So etcd-ctl, I can now get on 104 here, foo, and bar will be there. It has this watching primitive, so I can go /watch. Now this is an HTTP long pull, and can you see behind the transparent terminal there? If this works, etcd-ctl set/foo baz. You saw it kind of flip down, back, baz return. So that's that watching I was telling you about. It's all just HTTP, so it's pretty easy to dig into if you want to. Here's the keys in there. etcd-ctl is just a little HTTP client. It's talking to this thing. So that's good. You can also check like who the current leader is. So it's 107. So I'm gonna ctl. I'll explain this command in a minute, but I'm now on 107. I'm going to simulate an etcd failure by just killing the process. Okay, so if I kill etcd here, and I go etcd-ctl set/foo bar, it errors out because it's gone. And if I come back to this other machine and curl the leader again, we see now that it's 106. Because what happened, the master election occurred, a new master was created, or elected, and we are off to the races. Was I on 106 before? I wasn't. But if I start etcd again, and I can set foo bar, the cluster's up again. If I check who my current leader is, it's still 106. So that instance came up, rejoined the cluster. The old master stayed because it had been elected and there's no reason to do a master election, and the process continues. Okay? So that's etcd in a nutshell. There's more commands and stuff, but that's kind of the idea. So you would go like etcd-ctl set/db master is my IP through 306 or whatever. Okay, and then your applications could read that key to figure out what they need to do. You could also, if you don't want to modify your application, you could put like a proxy next to it that knows how to read those variables and send you off to the right place and so on. Okay, so that's etcd. Another chance? No? All right, yeah, right here. You can just ask.
Yeah. So you mentioned when you shut down etcd there, it did a master election or whatever and picked a new master there. Is there a way to configure it to automatically spin up another node that will serve as the master? This would probably be more for when you have fewer clients running there. So like if you only had one node in your cluster or two and one of them goes down, so you don't have failures and stuff like that.
Yeah, you could write it. I mean, the way it's meant to be used is you have a set of machines that are acting as the quorum, and it's okay if one goes away. Now, if you know that the cluster, if it's gone forever, like you could bring up another machine and add it to the cluster to tell it to start using that other machine. But it's actually part of the consensus algorithm to know if a machine is gone or not. And since that's in like non-deterministic, the machine could be gone for 1 minute, or is it going to be gone for 20 minutes, or is it gone forever? Without an operator doing something, you can't really make that determination. So the point is you can actually run 4 out of 5 nodes just fine, assuming that that will get backfilled at some point with that machine rejoining. etcd in and of itself, doesn't talk the Amazon API or anything, so it can't just spin up a machine. But you could write a system on top of it that like implements that logic relatively easily, because it does advertise all the peers and who's active and all that kind of stuff. Okay, systemd. Go into systemd for a minute. Okay, so systemd. I'm going to write the most basic systemd service file just so you can get an idea of how this works. I use my sleep demo again. Oops. There we go. Okay, so this is about as simple of a systemd unit file as you could possibly write. This is a daemon that sleeps for 3,000 seconds. Okay, so systemd is your init system. So it's your alternative to running commands like this. Who remembers running this one, or still probably runs this one, right? Yeah. And then Red Hat innovated, and it was service Apache 2 start, right? That's the Red Hat one. Ubuntu blew our minds. What? You could just call it start? And then we are now in 2014, and we call it systemctl. So we've done it. Finally figured it out. In this case, I could go start sleep, and that started my sleeping daemon. I can go status sleep and see what's going on. We see the process is running. Systemd is a supervised init system, which means it doesn't just fork the process, it also monitors it. So if the process was to crash, it could do things like automatically restart it for you if you want. It also has built-in logging. Like some of the nice stuff about the built-in logging. This is where people get a little bit like systemd is doing too much, but I'm kind of like, come on. So this is the journal. This is the log for this process. There's not a lot of log entries just starting and stopping because this thing's just sleeping. But because, again, we're in 2014, you can output to JSON now. And it's like this is where, again, folks are kind of like, whoa, systemd does too much. But it's also kind of like, man, the first thing we do with our logs is like write some Perl script to put it into JSON or put it into some other format, So it's like, why not just provide a native facility to do that? And, this is where, a heated Linux debate. If you care too much about your init system, you might be worrying about the wrong things. So systemd works well, but this is the basics of systemd. Okay, if I could stop it, so on. Whoops, not systemd. Wrong one. And then status it again, and you'll see it's loaded but inactive. Okay, make sense? Good? All right. So let's do a fleet one instead. So I'm going to write another one. I don't know why I didn't just copy that, but I'm just going to type it again. Do the same command. If I wanted this to be a Docker command, for instance, I would just go user bin docker run busybox sleep 3000. This would download a busybox container and run sleep in there instead of on my host sleep, okay, to write my stupid daemon. The only reason I'm not doing this is because I would have to download that Docker busybox thing in order to get it to work, and it would mean I'd have to try to fish jokes out of you guys again while the thing downloads. So I'm just going to have it sleep there instead. So where I had systemctl, now I have fleetctl. And I'm going to go start test.service. So this is going to schedule it against a machine. Look, it landed on 108, even though I'm running on 107. So if I fleetctl ssh test.service, oops. I am now on the machine that's actually running that, so I could go test and see. Ooh, How does my sleep service die? That's surprising. Fleet CTL list units. Yeah, that's crazy. I typed what? Oh, did I just type the wrong command? Fleet CTL cat sleep. Oops, it's a test. Oh, okay. Well, that's unfortunate. Yeah. Well, it ruins the next part, though, so we'll try again. You're running out of time, so I just want to get to the punchline here sooner than later. I gotta get that faster. Okay, so now it's running on 106, Fleet CTL status. We'll see how test 2 is doing. I keep doing that. It's because I'm bouncing around the cluster and the thing is going. Okay, look, it's running now, so we're good. The thing I want to show you here is if I go to where test 2 is running, systemctl status test 2, okay, it's good. Now I'm going to kill this machine. I'm just going to power it off. All right, so I flip back from 106 to 108. I just powered it down and lost a node. So if I fleetctl list machines, should only have 4 now. Yeah, I only have 4 hosts. And then if I list units, that is now running on 105, where it previously was on 106, right? Magic trick. What do you guys think, huh? Yeah? Woo! All right, so we could schedule, we could start scheduling these across a bunch of machines. Let's say I want to, I'm going to teach you guys also some bash expansions for those that are into that kind of thing. Bash has been a popular topic recently. So that just copied this unit a bunch of times for me, and then I'm going to fleetctl start. I'm just going to rm to make these commands easier. Test 3. Okay. So this will launch these set of things across, the whole thing here. Go. I wish it was faster. Come on, I got to talk to the guys about that. Okay, so that's running across a set of machines. You'd see that they're just kind of randomly spread around to different hosts. If I wanted to, I could say launch a new service. I'm going to just copy one of these to save me some typing. That says things like xfleet. I think it's xconflicts still in this version. So this is saying, don't run me anywhere test 3 is running, or better yet, don't run me anywhere test star is running. Okay, so this allows you to schedule like an anti-affinity mode. So you could schedule like 3 of these units, and you'll be guaranteed that they won't get scheduled to the same hosts, for instance. Okay, so we'll see if anything. Tests are running across a bunch of the machines, so I don't actually know if this will be able to schedule because test is already running on everybody. Does that make sense? Because see how test is in there, on all the different hosts. So it's just not able to schedule. So how could we get this thing to schedule? Any ideas? Take the line out. Clever. Any other ideas? Not Cole. You're cheating. No? Core up. We're going to launch another machine. So if I go back to, where was my terminaling the core up thing? Here it is. Core up. I'm going to do provider equals EC2, run. Let's give it 4 more machines. Cloud config equals that core update. And now this is going to sit and run while we do that. That lied. That's a bug. It printed out the previous machines that were already running. But those 4 machines are now running and being launched. And if we give it a minute, this thing will get scheduled at some point here. Oh, did those really come? Oh, sorry, I thought those were machines. I'm like, those came up real fast. Okay, there's still only 4 hosts going. While we're waiting, let's check this back out again. Yeah, see, here's the hosts that had registered themselves into etcd for part of the bootstrap protocol. This bootstrapping like if the bootstrap service went down, it means you wouldn't be able to bootstrap, but it wouldn't take down your existing running cluster. It's only used for the like initial bring up. We're making some changes to that, but this is just purely for ease of use, not like something we would consider what you should do in production, although that stops nobody from just deploying stuff into production and then depending on our hosted service. But did we get our 5th machine yet? Definitely could have if the network topologies would allow them to communicate. The way the etcd listens and everything, it just depends how I configured it. I don't remember what's in my cloud config, but if I said use public IPs, then yeah, it could. But now you'd have a public IP on the internet with a key value store that controls your init system. So you kind of want to keep that protected. But there's no technical reason why you couldn't other than the networks being able to talk to each other. But yeah, that would, and etcd supports TLS and client-cert authentication. So my cloud config would be a little bit longer in that it would have all the keys and stuff in it, but you could set it up such that I could speak across the internet, encrypted and everything, and properly authenticated and everything as well. Question way in the back? All right, TLS authentication. Hopefully that was enough. Yeah, it looks like it. Okay, list machines. Yeah, let's see all the hosts running, and then list units. And we should have foo running. Yeah, and then foo is now running on one of those newer machines, not any of the ones scheduled with test already. All right, make sense? Now we can just keep schlepping machines at it and see what happens. Let's tell this thing to run like, I don't know, 25. I don't know what my quota, dang, that's my quota on Amazon. My quota on Google is 4,000 cores. That's why I use that one. My quota is 20. Okay, well that's kind of boring. I guess I could launch like 8 more. What only allows 3 more running instances? Oh, okay, well, I launched 3 more and they would join. It's not that exciting. Let's launch them anyway. But that's kind of the high-level overview of all of this stuff. We are still, remember I started with the platform for building platforms. This is all pretty low-level things. This is not like Heroku. This is something you would build Heroku with. And so the UI is definitely meant for folks that are building sort of a higher order platform on top. And because of that, we've seen projects pop out. Like Deus is actually one that Deus is a PaaS that they build on top of Fleet and etcd and CoreOS, but it is like a Heroku type thing that you can run in your own environment. And that's definitely the intended use case here. So for building your own types of systems like this, as well as running your own infrastructure. Yep. I mean, technically you need like at least 3 servers. I mean, the startup guy in me says, make your infrastructure totally janky until your product actually has some traction. So like, don't go overkill on your infrastructure until your product has it. That said, if it was easy enough and this stuff was reliable enough that like it just kind of worked for you, it's like, why not? You know, the only reason you wouldn't do it is because it's too hard or it doesn't work. And so I'd say at this point, if you have a really small project and you're trying to commercialize it or something, just like make that work and make your users happy, and however you run it doesn't really matter. But if you're doing it from like a spirit of I'm building something that's like I know is going to have meaningful traction sooner than later, like let's say you're doing it on behalf of a big company or something that already has the load, then you might consider these like architectural patterns, because it's hard to change an application unless it's hard to change an existing running application that's sort of doing it the old way to run it this new way. And so having that in mind up front would be helpful. But if it's just like your side project for school or whatever, it's probably overkill. Yep. So that concludes my demo. I guess we killed, let's see if they got all my terminate requests. That's one trick that Google has as well, is they'll quota your terminates too, which is a problem when you launch 1,500 servers, because it actually costs you real money. Whoops, terminal issues. Anyway, I'll get that sorted out afterwards. Thank you guys so much for your time. And if you have any other questions, don't hesitate to come ping me. Thank you. And I have CoreOS stickers if anybody wants them.